Good morning, everyone. Well, here we are. We're at our last unit for data, probability distributions, and this is our first lesson. So hopefully, we keep plugging away and we get all of this in before the end of the school year. Everything seems to be looking great in terms of timing, so I'm not worrying at all, guys, okay? All right, let's take a look. We're dealing with a probability distribution. And let's break it up into the words probability and then into the word distribution. You know what the word probability means. We've spent an entire unit. Probability is always a fraction with the desired over the total outcomes. We're very familiar with that idea, a variety of ways. It could be a permutation probability, combination, selection, but the general consensus is desired outcomes over total outcomes. Now, how are things going to differ for us? And the way things are going to differ is this with this word right here. The word distributions looks at all possible outcomes to a situation rather than a single event type of outcome. Now, I know that probably sounds fuzzy, but don't worry, we're going to look at some examples here today and we're going to clarify it. So let's take a look at the first little block of material. It says a probability distribution is either a table, a graph, or an equation, most cases a table, that illustrates the probabilities of all of the outcomes, not just a specific outcome, all of the outcomes. And that's the most important concept. Discrete random variable is a variable that represents the outcomes. Again, might sound fuzzy. Don't worry, we'll pull it together. Let's look at some common examples, and this is where things are going to be pulled together. Let's look at the situation where I have a single die in my hand, and you can envision it, one little dice sitting in my hand. In the probability unit, I might word a question to you, what's the probability of rolling a 6? And you would know that there are 6 sides on the die, one of them being a 6, so the probability is 1 over 6. That's a probability question. A probability distribution says, no, don't just look at one specific particular outcome. Let's look at all of the outcomes for that imaginary die. Well, I could roll the die and get a 1. I could roll the die and get a 2. I could roll the die and get a 3. I could roll the die and get a 4. I could roll the die and get a 5. I could roll the die and get a 6. So all possible outcomes are listed in the outcomes part of the chart. Now, the probability of each of those outcomes happens to be 1 over 6, 1 over 6, 1 over 6, 1 over 6. These are what we call the associated probabilities. Okay, let's do another one. Flipping a coin. Well, if you could envision a coin in my hand, you know that there are 2 possible outcomes, heads or tails, and the associated probability is a half and a half. Associated prob, all outcomes. Okay, let's take a look at another type of question that we're very familiar with. We're familiar with the dice chart. We've been doing the dice chart. Now we're in Unit 3 of looking at the dice chart. So let's think about my outcomes. Now my outcomes are the possible sums. So I could have a sum of 2, a sum of 3, a sum of 4, 5, 6, 7, 8, 9, 10, 11, or 12. These are all of the possible outcomes if myself and another person played the dice game. Now, what are the probabilities, the associated probabilities? Well, I know that for each of these options, my NS is going to be 36. Because every time I'm in a dice chart question, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm a little bit off there. Okay, so I'll do a little arrow. So probability of rolling snake eyes is 1 out of 36. Probability of rolling a sum of 3 is 2 out of 36. A sum of 4 is 3 out of 36. A sum of 5 is 4 out of 36. A sum of 6 is 5 out of 36. 1, 2, 3, 4, 5. A sum of 7 is 6 out of 36. A sum of 8 is 5 out of 36. A sum of 9 is 4 out of 36. A sum of 10 is 3 out of 36. A sum of 11 is 2 out of 36. And a sum of 12, sorry guys, is 1 out of 36. So for each of these charts, what you're looking at is what we call a probability distribution. You're looking at all of the possible outcomes and all of their associated probabilities. All of the possible outcomes, all of their associated probabilities. All of the possible outcomes to this particular type of question, all of their associated probabilities. Kind of neat, okay? Now, let me show you something else here for a second. If we go back to this particular question, and I see that all of the probabilities are the same, if I was to graph it, okay, my bars would all have the same height of 1 over 6. This is what we call a uniform distribution. It's a distribution where all of the probabilities are the same. If I was to graph the second one, I would have 2 bars, a heads and a tails bar, and because the probability is exactly the same, they would have the same height, and this again would be called a uniform distribution. Now, things would be a little bit different here. And the reason that things would be a little bit different is because when I'm taking a look at my probabilities, 1 out of 36, 2, 3, 4, 5 out of 36, 6 out of 36. Oh, so I'm kind of climbing, reaching a peak, and then dropping. I'm hoping that this picture looks familiar to you because it's actually allowing us to reference back to the first part of the course, and this would be called a normal distribution. A bell curve, a mound, a normal distribution. Now, what we notice in the normal distribution is that, there's a peak in the center. And can I ask a question? Where is that peak occurring? Where is the high point in terms of the probability? That's at a sum of 7. Okay. Keep that all in mind, guys. Next question is, right at the very bottom of the note, what is the expected sum when rolling the dice, and how would you know? So if we played this game over and over and over and over and over all day long because we're bored in quarantine, and myself and another person played and we kept jotting down our sums, what do you think the most popular sum would be jotted down on that piece of paper? 7. And why would you expect that? Because it has the greatest probability. Very, very logical. Okay, it makes sense to us. So, what have we discovered on this first page of our note? We have discovered that a probability distribution is a chart, a table in which all of the outcomes are listed as well as their associated probabilities. And a probability distribution can sometimes help us determine what we would expect from playing this little game. What would we would expect to occur. Okay, let's flip when you're ready, please. Okay. Finding the probability that the sum is 5 is a very specific probability. So if I said to you, hey guys, dice chart, what's the probability of a sum of 5? Very, very specific. You draw the dice chart, sum of 5, 1, 2, 3, 4. Out of the 36, probability is 1 over 9. That's what we did in the probability unit. Finding the probabilities of all of the possible outcome to a dice question is what we call a probability distribution, because we're listing all of the outcomes and all of their associated probabilities. Now, let's talk about this notation right here. You're very, very clear that the P represents probability. We've been using that. The X, large X, is the criteria. So in this case, it would be sum equals, and in the small x is the number of times that we want to meet it. So in our particular example, we often used words when we were doing probability questions. Probability sum of, right? But you could algebraically represent it where x represents the sum, equal represents the of, and 5 represents the 5. Okay, just a different notation, just so that you're aware. All right, let's jump into the next thing. And this is the first major topic and types of questions that you're going to see on the test. Expected value. Expected value is the predicted average of all of the possible outcomes. Predicted average. Don't lose track on that word. Average value of the discrete random variable. It's the outcome that you would most likely expect. So the outcome that you'd most likely expect, but it's a predicted average. Now, what goes with it is this beautiful formula here. And I apologize if this was not in your note. It might have been the fact that my equation editor didn't have all the little pieces that I was looking for. So maybe take a moment. I can't remember whether it was blank or not blank in your note, okay? So the formula for expected value is the summation. You know that summation from the first term to the nth term of the actual value of the outcome times its associated probability. So it's the summation of the value of each outcome times its associated probability. Now, how does this work? How does this work? Well, let's go back and revisit this example. What is the sum, or what is the expected value of the sum of two dice? We already know the answer. We already know that answer. we know that that answer is 7. We were able to logically see it right here from the probability distribution. But let's pretend that we didn't, and let's pretend and use this formula and see what we can pull together. So hold on, what does the formula say? It says expected value is each outcome times each associated probability. Each outcome times each associated probability. So outcome of 2 times its associated probability. Outcome of 3 times its associated probability. Outcome of 4 times its associated probability. And I'm just going to keep that pattern going. So I'm following the formula, and the formula says, please sum up the outcome times the associated probability. I'm almost there. I'm almost at my outcome of 12. Okay, everybody with me? I'm going to take my red pen and I'm just going to put a 1 underneath because I don't want to mess up my fractions. Okay, so I am going to have 2 over 36, 6 over 36, 12 over 36, 20 over 36, 30 over 36, 42 over 36, 40 over 36, 36 over 36, 30 over 36, 22 over 36, and finally 12 over 36. I hope we can see that. Okay, so all of them have the same denominator. So that means I'm going to have 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12. And that gives me a grand total of 252 over 36. And guess what? When you divide that out, bingo bongo. Therefore, the expected sum of the dice game is 7. Now, does that mean that you're going to roll or get a sum of 7 every single time? No, you might get a sum of 12. You might get a sum of 2. You might get a sum of 4. But the most common, the most likely expected sum is 7. The predicted average is 7. Very, very classic question. Okay, when you're ready, and I apologize, I know that this is hard because the pages, I'm spreading out so wide on the page. When we're ready, we'll flip and we'll get into some good homework and test questions. Okay, let's take a look. What is the expected number of heads if you flip a coin 3 times? Now, before we get into this question, I want to talk about the difference here. The last unit, your questions would say something like, what is the probability of flipping heads? What is the probability of getting exactly 2 heads if you flip the coin 3 times? What is the probability that you'll have more tails if you flip the coin 3 times? Okay, this is very different. This is saying to you, if I flip the coin 3 times, what is the expected number of heads? Would you expect no heads whatsoever? Would you expect 1 head? Would you expect to get all 3 heads? So let's start again. A coin toss always starts with our very classic tree diagram. I don't know why I decided to put arrows this time on my tree diagram. I'm sorry about that. That's not my usual. Okay, beautiful tree diagram. Don't need to talk about it a lot. And again, the next thing that I don't need to talk about is the whole idea of the outcomes. We've been doing that. It seems like forever, guys, I know. Okay, now, you've done basically just some grunt work. You haven't answered the question by any stretch. The question says expected number. So expected number means that I'm going to have to run my expected value formula. But in order for me to write my expected value formula, I need a probability distribution chart. So these two things go hand in hand with each other. So let's think about all of the outcomes. I've got a coin and I'm flipping it. So I could end up flipping that coin 3 times and not getting any heads whatsoever. I could end up flipping that coin 3 times and getting just 1 head. I could end up flipping that coin 3 times and getting 2 heads. Or I could end up flipping that coin and, unbelievable to me, you, and everybody else, I could get 3 heads. So these are all of the possible outcomes to my game. Now I have to list their associated probability. Well, with their associated probability, we don't shy away from the whole idea of NA and NS. Your NS is your total outcomes. Your NA is your desired. So how many out of the 8 had 0 heads? How many of the 8 had 1 head? How many of the 8 had 2 heads? And how many of the 8 had 3 heads? Notice how these probabilities, 1 over 8 plus 3 over 8 plus 3 over 8 plus 1 over 8, is always going to give you 100%. Now that I've got the probability distribution table, I can very easily run the formula. Outcome times associated probability. Outcome times associated probability. Outcome times associated probability. Outcome times associated probability. Let me put my little ones. Denominator is going to be 8. 0 plus 3 plus 6 plus 3. 12 out of 8, 1.5. Now, is it possible for you to have 1.5 heads? Absolutely not. So therefore, the expected value is approximately 2 heads. Therefore, the expected value is approximately 2 heads. So notice what's required of you in an expected value question. Probability distribution chart with all of the outcomes listed and all of their associated probabilities. Expected value formula with a beautiful therefore statement. Okay, let's do another one. A prize table has 3 prizes worth $50, 2 prizes worth $25, and 5 prizes worth 10. Now let me give you a scenario. I go to a Stag and Doe, and they have a prize table, and on the prize table are these plain manila envelopes, and from what I've been told, there's money in the envelopes. Now, I've been told that over at the table, 3 of the envelopes have $50 in it, 2 of the envelopes have 25, and 5 of the envelopes have 10. Now let me think about that. 3 envelopes, 2 envelopes, and 5 envelopes. So in total, there's 10 envelopes. Okay, that makes sense to me. What is the expected value that is to be selected? Okay, what you need to understand that expected value doesn't mean that if Jody Martell walks up to the table, Jody Martell could walk up and walk away with the $50 and be the luckiest girl there. Jody Martell could walk up and walk away with 10. And some of you might say that's probably the most likely on an individual selection. But don't forget, expected value is an average. It's not a one-shot deal. It's not pretending that you're walking up and saying, I know a lot of my math brains in the class are saying to me, well, there's 5 $10 bills, Miss Martell. You're probably going to get $10. I know that. That's on an individual walking up to the table and then walking back to your expected value. Plays the game as if you were playing it all day long. I was going up and back, up and to the table and back and forth, playing it all day long. It's an average. So let's create my chart. My outcomes are that I could win $50. I hope so. I could win $25, or I could win 10. Now, the associated probability all has an NS of 10 because there's 10 envelopes sitting on the table. 3 of them have 50, 2 of them have 25, and 5 of them have $10 bills. So yes, if we were just walking up to the table once to pick a prize, I know that I'm probably going to walk away with the $10, but that's not what expected value is asking. Expected value is asking what would the most likely option be if I played the game repetitive times, and it's your average. So outcome times probability plus outcome times probability plus outcome times probability. 150 plus 50 plus 50. 250 divided by 10. Therefore, your expected value on an average is 25. Oops, sorry guys. I desperately wanted to win that 50. Is $25. And I know this example causes some people some grief because they say, well, wait a minute, Miss Martell, that's not really going to how it happen. That's not going to be how it happens, right? I agree with you. If we were just walking up to the table once, you're probably walking back with the purple bill. But the fact that expected value is an average and you're playing the game multiple times, the average is, I'd have some 50s, I'd have some 10s, it would average out to probably your expected value of $25. Okay, please make sure that's clear in your head. Okay, when you're ready, let's look at another common example. A game consists of tossing 2 coins. I'm going to draw the tree diagram. Okay, you win $1. Oh, sorry. If the result is 2 heads, you win $1. If the result is a head or a tail, you win 50 cents. And if the result is 2 tails, you lose $2. So you're just playing a little gambling game, you and a friend. Okay, let's take a look at our outcomes. They're asking for expected value and our probability. Well, we could play and get heads and be up $1. We could play and get heads-tails and be up 50 cents. We could play and get tails-heads and be up 50 cents. Or we could play and get tails-tails, and that's going to cost me $2. Now, what is the probability? Well, this is a uniform probability because my NS for each of them is going to be 4. 1, 1, 1, and 1. Uniform probability. So my expected value is going to be 1 times 1/4 plus 50 cents times 1/4 plus 50 cents times 1/4 minus 2 times 1/4. So outcome times probability, outcome times probability, outcome times probability, outcome, careful, times probability. So denominator is going to be 4, 1 plus 0.5 plus 0.5 minus 2. 0 over 4. My expected value is that I'm not going to make any money. I could play one game and be up $1. I could play one game and be up 50 cents. I could play one game and be down $2. But the idea is with the averaging, if I played the game all day long, my ups and downs would all balance out and I would be breaking even. Next question, really, really important, and I want you to listen to me clearly. Is the game fair if I told you that it costs you 25 cents to play? So if every time I play the game, it costs me 25 cents to play, and my expected value is 0, is the game fair? Now, when you are asked about fairness, I don't want to hear things like, no, it's not fair because I'm going to lose 25 cents. That's not what I want to hear. I want to hear that, no, the game is not fair for one reason and one reason only. Because the cost doesn't equal the expected value. Sometimes you might be on the end of losing money, so it's unfair because you're losing money. Sometimes you might be on the end of it being unfair and you're making money, but it's still not fair. Okay? Fair is fair to everybody, not just you. So when you're asked, is the game fair? I don't want a lengthy explanation. The explanation is yes or no for this reason and this reason only. Please, please, please hear me on that, because you'll lose marks. Okay? A game is fair when the cost equals the expected value. Anything else is unfair. And I don't need to hear all the rationale. This is the rationale. Okay? All right. One last example. If we randomly select 4 students from our class to help out on grade 8 day, what is the expected number of girls? Okay, so I'm going to do my hypothetical again, and I'm going to say that we have 25 students in our class, 10 boys and 15 girls. This would be, normally I would survey. Now, hold on, let me read it again. If we randomly select 4 students from our class To help out with grade aid day, what is the expected number of girls? So randomly selecting 4 students. So I put everybody's name in a bowl and I start picking out some names. Well, I could end up with the situation of actually no girls whatsoever. I could end up with all 4 boys. I could end up with the situation of having 1 girl and 3 boys. I could end up with the situation of 2 girls and 2 boys. I could end up with the situation of 3 girls and 1 boy. Or I could end up random with 4 girls. I don't know how it's going to end. The names are in a bowl and I'm, scooping them out. Probability. Now, what's so great about this unit is we pull on a lot of stuff that we've done before. So if I'm looking for an associated probability for each of these, I've got to look at, well, what type of question is this? We've seen a coin toss, a couple coin tosses. This seems to be like a combination. 25 choose 4 on the bottom. That's the no restrictions. And on the top is going to be what's desired. So hold on, I'm going to have to get my calc out. So just give me a second while you guys are writing. I'm going to do the combination of 25 choose 4. Whoa, just happened there. $12,650. Now, the desired, the top says 0 girls, so 15 choose 0, 10 choose 4. 15 choose 1, 10 choose 3. Top number adding to 25, bottom number adding to 4. 15 choose 2, 10 choose 2. 15 choose 3, 10 choose 1. Again, top number adding to 25, bottom number adding to 4. 15 choose 4, 10 choose 0. Okay, so you're going to have to give me a moment here. 15 choose 0, 10 choose 4. Whoops. 210. 15 choose 1, 10 choose 3. 1800. 15 choose 2, 10 choose 2. 4,725. 15 choose 3, 10 choose 1. 15 choose 4, 10 choose nothing. Now, as a double check, let's take these 5 numbers and they better add up to the 12,650. Okay, so I'm just double checking. 210 plus 1,800 plus 4,725 plus 4,550 plus 1,365. And I got my beautiful 12,650. So I know that I didn't have any calculator errors. So right now I've got my probability distribution chart. And now I'm going to do my expected value. Outcome times probability. 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 Because that's what expected value wants you to do. Okay. Bottom number is going to be the 12,650. 0 times 210 is 0. 1 times 1800 is 1800. 2 times 4725, 9,450. 3 times 4550, 13,650. And 4 times 1365, 5,460. So 0 times 210, 1 times 1800, 2 times 4,725, 3 times 4,550, 4 times 1,365. And add them all up. Give me a moment. Divide now. .4. Now, you can't have 2.4 of a girl. It's not possible. Okay? Just like you can't have a portion of a coin or whatnot. So this is approximately 2. So therefore, the expected number of girls is approximately 2. Notice that beautiful word of approximately. Okay? Sorry for this being a little bit longer. Some of the other lessons will be shorter, but this is a biggie. Hope this helps. Good luck on your work. Thank you.